Jeff received his PhD in experimental low temperature physics at the University of Wisconsin. He has been with the cryogenics group at NASA Ames Research Center since 2000, so 20 years now. He has worked on designing, building, and testing cryogenic refrigerators and components, and more recently, he's been playing a large role in the design and analysis of passive and active cryogenic propellant management systems. So with that, we'll go on here. Take it away, Jeff.
All right, thank you very much. I want to apologize in advance because I think I do have a few more slides than I actually need, so I will be skipping over slides as we go. Here is the our team members and consultants. Quite a diverse group, at least in terms of expertise. This is what we'll be talking about. First, we'll have an overview of the Stratospheric Observatory for Infrared Astronomy, that's SOFIA, and SOFIA science instruments that have been developed, emphasizing the various cryogenic components with flight heritage. We'll be looking at constraints on the SI. SI, by the way, science instrument. Sometimes I'll call it a cryostat. So these are all interchangeable, even though technically it's an SI, not a cryostat. So constraints on the SI, especially where they might impact the design and operation of the SI cryostat. So these include a lot of procedural constraints, which are dictated by the strict pre-flight and flight timelines. We won't go over too many of those. We just don't have time, but there are volumes going to that. Volume, mass, and center of gravity constraints, environmental constraints, including possible temperature excursions, and most importantly, vibrational environments. And then other things like cryostat tilt, which I'll explain later. And finally, a discussion of cryogenic refrigerators and other thermal control components, including their principles of operation, operating constraints, potential capabilities, flight heritage, and their overall applicability to future SOFIA SIs. So SOFIA is a modified Boeing 747. It's an infrared observatory, of course. Now, the problem with infrared is that the Earth's atmosphere is very good at blocking infrared. So to do infrared astronomy, you have to get above the atmosphere, or at least above most of it. And SOFIA can climb above 99% of the Earth's atmosphere. That's the whole idea of putting a telescope on a plane. Here is a nice little cutaway. You can see the telescope back here. The telescope, it can change its altitude. It rotates within this. And that is connected down by a tube that goes through this pressure bulkhead to a mounting flange. And the science instrument mounts to that flange. So as the telescope turns, moves, cryostat also tilts. And then over here, we've got workstations. Conference room over there. There's a nice little map that shows various SOFIA instruments, as well as a couple other instruments, including James Webb Space Telescope. That's this sort of olive footprint down here. Of course, that's still in development. That's a space telescope. And ALMA way over here in submillimeter. This is really a radio telescope, ground-based telescope array down in Atacama Desert. And then the rest are SOFIA instruments, science instruments. Hermes, the dotted line indicates that it was still in development at the time this chart was, this figure was made. That has recently been canceled altogether, unfortunately. Well, there are still gaps in here that need to be filled by future instruments, and hopefully that will happen. Now I'm going to go through some of these instruments, and for each of these there's a table like this, which we won't spend too much time on. It has a lot of technical details about the detectors and filters and so forth, which we're really not concerned with in this presentation. It has no bearing on the cryogenics. Excuse me. So we'll go right to a picture. So this is what's called forecast. And these names are all acronyms, of course, like everything in NASA. And this is a relatively simple SI. It's cooled by liquid helium. It also has a liquid nitrogen can, which is used to intercept heat, thermal radiation, conduction down wires, and so forth. And then the instrument is mounted to a cold plate that's in contact with the helium. And on the left, you can see where it mounts to the forward end of the telescope assembly. That's this blue part back here, and this is the mounting flange. This is forecast mounted to it. TFAWS, this is another liquid helium based cryostat. It has a liquid nitrogen jacket, which is this red. It has liquid helium tank, which is this blue. Instrumentation is down in here. But it has another, a second liquid helium vessel. And this, when it's operating, it's being pumped on. And when you pump on helium, or any liquid for that matter, it cools down. So in this way, the detector can be cooled to around 1.8 Kelvin, pumping on that 3.1 liter helium tank. And it becomes superfluid, but it's really the temperature that we're concerned about. A mechanical scroll pump is used. This is a permanent fixture on SOFIA. It's sort of a general purpose pump, but in this case, it's used for pumping on that little vessel. A hold time of 18 hours is achieved, which is more than enough. Finally, great. This, what I've showed you so far are what are called wet cryostats, which means they have liquid cryogens, liquid nitrogen, liquid helium, superfluid helium. And these are, and these cryogens eventually boil off. So that's what limits the observation time of the telescope. Now, in this case, there are no liquid cryogens, so it's referred to as a dry cryostat. Actually, several. They're little cryostats that plug into this chassis here. So instead of liquid helium, what's used is a pulse tube refrigerator. Just a commercially available pulse tube refrigerator, 2-stage. And the second stage gets down to 4 Kelvin. So without using liquid helium, you're getting the detector down to 4 Kelvin. And it's pretty much just a plug and play cryostat then at that point. Here's a close-up on the right. You have 2 of these channels or cryostats installed. These are vacuum cans down here. Up here, this is one of the pulse tube cold heads. Another one sticks down into the cryostat. Here shows the instrument turned around, and you can see the open cavity the open tube going towards the telescope itself. So this is the mounting flange on the forward end of the telescope assembly. So, like I said, this is the first dry cryostat. Each cryostat uses a commercial low frequency, few hertz, 2-stage pulse tube cold head. Initially, a Sumitomo helium compressor was installed especially for this. Later on, Sophia made the decision to install permanently 2 compressors, which could be used by future instrument developers. So the cryocooler infrastructure is now an observatory mission system that is available for use by anybody now. Okay, Hawk Plus, now we're getting very complicated. This is another wet cryostat, but it has a surprise hidden inside. It has a magnetic refrigerator with a I will talk about what this is. I don't expect anybody really to know what this is yet, but we'll talk about it later. This is a magnetic refrigerator. It was supposed to get down to below 100 millikelvin. So much colder than anything before. It actually runs around 180 Kelvin, if I remember correctly. There were some problems with vibrational heating on this cryostat. This we don't have to look at, I guess, just another view of the where it sits inside the cryostat. So Hawk Plus, this is the first sub-Kelvin science instrument. The first to use an adiabatic demagnetization refrigerator, or ADR. To date, it's the only one that's used in ADR. It was built by Goddard, provide cooling down to, I say below 1 Kelvin. It's really around below 200 millikelvin. Also, it used a helium-4 absorption refrigerator. That's something else we're going to talk about later, as well as a helium-3 gas gap heat switch. And finally, we have Hermes. This is the one that was canceled. It's too bad because it was a very ambitious cryostat. It's similar to Hawk Plus in that it uses an ADR, which is down here, but this is completely dry cryostat. There's no liquid helium or liquid nitrogen. That job is taken up by 2 pulse tube coolers, the same coolers that were used in the great instrument. So here's one of them. The other one is right next to it. It's not shown. So they also had, this program also had problems with vibrational heating, other problems as well. I won't get into it. Anyway, it's still a very interesting example to look at. So I'll be referring to it at several points in the presentation. So like I said, it was the second sub-Kelvin SI. So project was canceled. So that's the last one I'm going to talk about. There are retired instruments, which you can read about if you want by following the links. Now, we'll get into SOFIA operations, and this is about this is all about various constraints on the SI. So we start here. The first bullet just recapitulates something we just said, some things we just said about the 747. Second bullet, SOFIA flight operation normally based out of Armstrong, down in Palmdale. And in addition, they periodically take trips to the Southern Hemisphere. And Christchurch, New Zealand is their Southern Hemisphere home. That's generally 2 months out of the year, I think. This one you won't say too much about, but it just shows a sort of notional schedule, flight schedule for a plane for SOFIA. Sorry. Starts with takeoff, level off to observing leg number 1, observing leg number 2, and so on. The reason we keep climbing in the staircase pattern is because as you use fuel, you can climb higher. So later in the observation, you're at higher altitudes and you descend. This is about 10 hours total. The observing time, 9 hours. And this isn't just another, we won't really talk about this, just another notional schedule, pre-flight schedule. There's a lot of stuff going on. That's the thing to take away from that. Cryostats environments during deployment. The first one, deadheaded, non-operational. This is for trips to the Southern Hemisphere. So they would typically have a science instrument in the cargo hold as well. And SI labs at deployment operations site, they're often more rudimentary than home facilities. There are diversions to alternate landing sites, sometimes due to poor weather. And then it's always parked on the tarmac unless it's home in Palmdale. SOFIA typically does not have access to protected accommodations, e.g. hangars during deployments. So this could be a problem in the summer because it can get quite hot parked out on the tarmac, and especially can get very hot in that cargo hold. And we'll talk a little about that in a few charts as well. This is just the main cabin temperatures. This doesn't have too much bearing on the design of the cryostat. The temperatures range from 55 to 85 Fahrenheit. So it can be somewhat uncomfortable at times, but that's about it. The cargo hold temperatures, this is potentially a different story. The maximum recorded temperature in the FLL stands for the forward lower lobe. The maximum recorded temperature there was almost 100 degrees Fahrenheit. Minimum recorded temperature is 51.8 degrees, which I don't think is a big problem. But the upper temperature could be a problem, as there are some components on some SIs that could be damaged by such heat. And that includes salt pills and ADRs, entrance windows. And there's no air conditioning down there. So this is sort of an ongoing problem that they're trying to address. Electrical power distribution, we don't need to talk about this. There's a 6.5 kVA allocation for the SI itself. And it's important to note that this does not include the compressors for the pulse tubes. Those have their own power source, 20 kVA power dedicated to them, to the both of them. Mass of the science instrument. The SI maximum mass 600 kilograms. It is possible to get waivers, I guess. That's been done. I believe Hermes got a waiver before they were canceled. Anyway, and then there are for center of gravity and so forth. There's there are other constraints. Volume constraints as well. You don't want it banging into anything. You want to be able to get it in the door, for example, which can be tricky sometimes. Now, the Sophia crowd cooler system. What this is really is mainly those two compressors that I talked about, the flex lines that connect those compressors to the pulse tubes at the SI, and then there's a frequency converter, power converter. So just to give you the history of this, the first generation SIs used expendable liquid cryogens, and actually up to now there's only one SI that did not use expendable liquid cryogen, and that was the great instrument. The first generation SI PFI, like I said, it used this vacuum pump system to pump on a helium bath, got down to 1.7 Kelvin. Several newer channels on the great SI use pulse tubes. And now when it flies, it uses this Sophia crowd cooler system. So third generation Sophia SI Hermes would have also used this system. So to support the cooling needs of these newer SIs, the Sophia program implemented a facility crowd cooler system comprised of two modified COTS liquid-cooled helium compressors capable of driving two selected SI-provided cooled heads. So what that means is that the compressors are provided by Sophia. The cold heads are provided by whoever is building the SI. Now, here in the center, these gray boxes, those are the two compressors that I was talking about. For each one, you've got two helium flex lines coming off that go down to the SI. By the way, this is in the space that's directly above the main deck. Over here is the frequency converter. You have to convert from, I think it's 400 hertz. Yeah, let's see, 400 hertz, three-phase, down to 60 hertz, three-phase. And then there's a control panel here as well. Down at the other end, so those flex lines are very long. They have to come all the way down to the back of the plane here. Not only that, they have to wrap around this big wheel, which is called the CLA, the cable load alleviator. So it wraps around that. So that the reason for that is when the mirror turns, these lines don't get all tangled up. So it comes in and comes to this patch panel, and when you're installing an SI that has that's using one or two pulse tubes, I should say. You would patch into this patch panel here, and that's what's shown here. We got additional flex lines going from the patch panel to the crowd cooler. Here's one of the pulse tubes shown here. That's the great instrument again. We won't talk about this, I don't think. And then finally, airworthiness constraints. This mainly is, for our purposes anyway, is mainly refers to pressurized systems. Like a pulse tube is a pressurized system, pressurized vessel, flex lines as well. And also sorption refrigerators, if you those are pressurized with helium when they're at room temperature. So those are potential safety problems. They have to be certified airworthy. Okay, so that is, I think, yeah, the first section. Now we go into the the vibration environment. Are there any questions on what I've covered so far? No? Okay. So what we got here, this is a drawing of the telescope assembly. Here's the mirror, the main mirror over here. That reflects light up to the secondary mirror, reflects light down to the tertiary mirror, which reflects light down this tunnel here, which goes through the pressure bulkhead, which is here, through the SI, which is bolted on here. Sorry, I've got a leaf blower outside my window right now. You can hear me. So this whole thing is mounted on bearings, and this shows. So if you look at the arrow U here, this whole assembly can rotate around that axis, plus or minus 20 degrees. And this is just another view of the telescope assembly with science instrument forecast bolted to it. Now, sources of vibration, pretty much what you'd expect them to be, light-induced vibrations. With the TA cavity door and gate valve closed, you got engine still, turbulent airflow, what we passengers usually refer to as turbulence. And there's pressure and temperature changes as well. When you open the cavity door and gate valve, you get typically an increase in turbulence to the exposed TA cavity. And as well as acoustic resonance inside the telescope tube, just like an organ pipe. And then there's effects of variable physical configurations, cause noise, vibrations. Variable telescope elevation position. Now, this is very important. The TA is equipped with a dynamic stabilization and vibration control system. It is very effective at attenuating frequencies above 100 hertz. And we'll see the evidence of that here. This just shows the various observation segments, and we don't have to worry about that too much. Now, there's been a lot of measurements of acceleration on the, especially on the TA assembly, the telescope assembly. And then sometimes when they mount an instrument, they'll attach accelerometers to that as well, at least at the tip of the thing. So in this photograph, there's no SI attached, so we drew in rather crudely a notional SI. This just shows the various locations of the accelerometers mounted on the system. And this we can skip over. Okay, so looking at, this is a good example to start with. This is flight segment 3, results only. Flight segment 3 is with, maybe I should have gone over that. Flight segment 3 is with the aircraft cruising at observation altitude. TA door is open and the telescope is tracking. So the telescope door is open. Oops, going the wrong way. So this shows all the resonant peaks. And you notice that dynamic stabilization active vibration control system really does work above 100 hertz. It dies down pretty quick. And a lot of data was collected above 150 hertz as well. So we know that this is all flat out here, at least on this scale. Okay. So this is for the instrument XEs. And this shows 2 sets of data. First set of data, which is the blue line, is for segment 1, which is before the telescope door is open. The orange line is for segment 3, which is after the door is open. So you can see the increase in turbulence comparing these red lines with the blue line. Okay, and this is comparing Hawk Plus to XEs. Different flights, of course. So not everything is equal, but nevertheless, there's still a surprising amount of overlap, considering how different these two instruments are. Now, the reason we're worried about vibration is because if you get some component at very low temperature picking up on one of these resonant modes, in other words, if it has a resonant mode, a natural frequency that coincides with one of these turbulent modes, you can get a lot of vibrational heating. And that can be mitigated by filtering and active vibration control. Like I said, this you've got the active vibration control, attenuating vibration beyond 100 hertz. Moreover, the structure of the cryostat acts as a filter and can further attenuate vibration. On Hawk Plus, there were spring washers that were inserted at the Kevlar suspension anchor points. It's greatly reduced the vibration coupling between the TA flange and the optical bench. And actually, I can show you a picture of that here. So this is the sort of inner vessel of the of Hawk Plus, and this is connected to the outer vacuum shell by these suspended by these Kevlar straps. And then there are these adjuster assemblies which you can use to adjust the tension. So that allows you to sort of tune the this filter. The other thing you can do is what I call tuning. You can decrease this is when you have a component like ADR salt pill, which is a small thing. with tends to have a fairly low resonant frequency. What you want to do is tune that so that its resonant frequency is shifted to preferably well beyond 100 hertz. And then in the end, there's damping. The energy pumped into a mode by the forcing function must either be dissipated in the component, internal or joint friction, which is bad because that would heat up the component, or you can damp it, which the way I'm defining it, that means it's dissipated at some higher temperature where the heating is more easily dealt with. And an example of this is the Hermes magnetic eddy current damper. And you have a picture of that here on the right. So this is the ADR. The salt pill goes in the bore of a superconducting magnet here. And connected to that is this damping mechanism. Sorry, connected to the salt pill is this damping mechanism. So this is very cold, around 100 millikelvin or something. And this bracket and the magnet itself is sitting at 4K. And there's a space in between here. So this is a magnet here, and this is just copper, I believe. So as you get vibrations here, the magnets will induce eddy currents, which will cause heating here, and it will damp down the vibrations. But the heating is okay because it's at 4 Kelvin. It's not at 100 millikelvin. So this is really only a problem at very low temperatures. And the thing is that at low temperatures, if you get into a situation like this, where you've got vibrational heating, it can be that very easily this vibrational heating can eat up all of your available cooling power. You're only starting with 1 or 2 microwatts of cooling. And you can easily get that much vibrational heating. So yeah, so if you're working at very low temperatures, you have to be very careful about vibration. And I'll skip over this one. Hermes design example. Skip over this as well. So that's covered very briefly the vibrational environment. Any questions so far? Anybody hear me? Hello?
Yes, sir. We can hear you.
Oh, okay. Just wanted to make sure.
We do have one question.
Oh, okay.
1 second. Lewis is getting that over. Okay. Monica asked from slide 48 to 49, is the vibration dampening requirement always assigned to the cooling system, such as ADR or cryo cooler, or is dampening applied to the instrument instead? Would this impact the heat load?
It is, well, it depends. It's applied to whatever is vibrating. Now, in this case, in this particular case of Hermes, actually Hawk had the same problem with their salt pill. Salt pill is just a sort of long cylinder that slides into the bore of this conducting magnet. This particular component has a vibrational mode that is, I think, around 100 hertz. That's that's the sort of the bare salt pill. Now, to stiffen that, it's inserted inside of a stainless steel tube, which pushes the resonant frequency up above well above 100 hertz. But still, there are other modes in that thing. So it's that thing that's going to be vibrating, at least in this case. Now, if there are other components that vibrate as well, you might want to consider putting some sort of damping mechanism in place to safely dissipate that vibrational energy. It's just that here, it's the salt pill that we're worried about. Does that answer your question? So, for example, if you had a component on the focal plane that was experiencing some sort of vibration like this, you could possibly think about damping that. Okay?
You know, we've got a slight delay between them asking and responding, but we do have another question.
Okay.
From JMT. She did say that, yes, that does answer it. The other question is they just asking for a simple example of vibration to heating, and also asked that you said it's only a problem at low temps. So where is that definition of low temps? Where does that start?
Oops. Okay. So low temperatures, I really mean down around where this ADR is operating. And it's not necessarily low temperatures. It's the fact that you don't have much cooling power at those temperatures. So like I said, with this magnetic refrigerator, both in Hawk Plus and in Hermes, there's only a couple microwatts of heat. A couple microwatts of cooling capacity, gross cooling capacity. So out of that, you have to take out all the parasitics. And one of the parasitics is this vibrational heating. So if the vibrational heating is 1 or 2 microwatts, well, that's going to eat up all of your available cooling capacity. So you might as well not have the ADR in the first place then, because you won't be able to get any useful cooling out of it. So that's what I mean by low temperatures. Typically, yeah, it's millikelvin range. There was another part of the question, I think. What was that?
Just a simple example of vibration to heating.
Okay. Well, this is a very simple example. It's just a simple harmonic oscillator. Imagine this. It's the equation of motion of a mass on a spring with a dash pot for damping. And then there's a forcing function as well. So this is just a one-dimensional problem with a single normal mode. And so imagine this mass moving back and forth. It has some resonant frequency, which is the square root of K, the spring constant, divided by the mass. If you've got vibrational noise coming into your system, that can couple with this normal mode, and you can very easily pump energy into it. So that'll cause the amplitude to increase until the damping can cause it to die down. So I make a distinction here between dissipation and damping. Dissipation is where that where that that vibration is damped internally to the, in this case, the mass and spring, which is where you wouldn't want to have it. So you'd want to connect, well, you'd want to tune this probably to get it out of the way of the vibrational frequency that's causing the problems. I don't know. I didn't explain it very well, I don't think, but but another good example is, again, the salt pill that has a bending mode that has caused a lot of problems with both Hawk and Hermes. Okay, I hope that helped.
Yeah, I think that's all of the questions, so we can move on to the next section.
Okay, so now we'll get into, I guess we're about on time. How much time do we have left? Is it an hour?
An hour and 10 minutes,
Okay,
yes.
So now we'll talk about an overview of the cryogenic components that are appropriate for SOFIA. This is sort of a brief history right here, this page. So first generation of SOFIA science instruments employed expendable liquid cryogenics. They were wet cryostats. Great introduced the two-stage pulse tube refrigerator, which meant that it was a dry cryostat. It used no liquid nitrogen or liquid helium. Hawk Plus introduced sub-Kelvin technologies, not just the magnetic refrigerator, but absorption refrigerator as well. The magnetic refrigerator was staged off the absorption refrigerator, which in turn was staged off of the second stage of the pulse tube. I'm sorry, not the pulse tube, this is Hawk Plus. It was staged off of the helium cold plate. Now, Hermes would have been the first dry sub-Kelvin SI, employing two pulse tube refrigerators, helium-3 as well as helium-4 sorption refrigerators, gas gap heat switches, and an EDR, which was very similar to the Hawk EDR. Now, this section assumes that the Hermes approach is a good approach. A dry cryostat based on commercial pulse tube or Gifford-McMahon refrigerators, and components that enable cooling to 4 Kelvin, 1 Kelvin, or down to 100 millikelvin or colder. And this is just a chart showing various types of refrigerators and their operating ranges, both in cooling power on the vertical axis, temperature on the horizontal axis. On the top, we have what are called primary coolers. Included there is a helium Dewar. These are called primary because you don't need another cooler to stage them off of. Pulse tube, you can plug it in and turn it on, and it'll cool down to 4 Kelvin on the second stage. Same with the GM. The other refrigerators have to be staged on higher temperature stages. So you've got the helium-4 sorption cooler, helium-3 sorption cooler, dilution refrigerator, multi-stage ADR, single shot and continuous, two-stage, single-stage ADR. And then this thing, NIS chip, which I don't know anything about. SOFIA cryocooler system can accommodate a wide range of pulse tube and Gifford-McMahon cold heads. Closed cycle cryocooler cold heads are available in both single stage and two-stage models. And looking at the third bullet, we really need a two-stage cold head. That's because the first stage of a two-stage cold head nominally approximates the temperature of a liquid nitrogen bath, 77 K or lower, depending on what the heat load is. Now, this would typically be used to cool the thermal radiation shield, which encloses the colder stages, and it's used to intercept heat loads carried by support structures and wiring. Second stage of the two-stage cold head can achieve temperatures of 4 Kelvin or even lower, again, depending on the heat loads. And it can be used to directly cool an instrument sensors, as in the great SIs, or to pre-cool colder stages, as in Hermes, which employed absorption refrigerators and an ADR. Thermal performance of a two-stage cold head is complex, has a large parameter space. So a lot of things can affect its ultimate performance. The heat links, the heat lift to the heat sinks on the first and second stages are not independent. So if you put heat on the second stage, that'll affect the temperature of the first stage as well. So pulse tubes versus Gifford-McMahon, they're very similar, except that a pulse tube has no moving parts except at room temperature, while the Gifford-McMahon, or GM, we'll call it, has a cold displacer, as in a Stirling cooler. It has often been suggested, at least I've heard people say this over the years, that the cold displacer introduces reliability issues, but I'm not sure I believe that's true. Both types are very reliable and require little maintenance unless they get contaminated, as with oil from the compressor. And the installed cryomech compressors have been modified to minimize that possibility. Now, for the SI developer, there are three main differences between pulse tubes and GMs. The first one is cost. The GM tends to be quite a bit less expensive. Second is dependence on orientation. The GM is insensitive to orientation or tilt. Remember, the cryostat has to tilt up to 20 degrees in either direction from the vertical. The GM doesn't care about that. The pulse tube does. There is a fairly strong dependence on deviations from vertical. And finally, there's vibration. There are three sources of vibration: the room temperature motor and valve assembly, pulsating helium in the thin wall tubing, and the cold displacer. That's for the GM only. The pulse tube doesn't have a cold displacer. GM refrigerators exhibit higher levels of vibration than similarly sized pulse tubes. So it's for this third reason here that pulse tubes generally are used for low temperature work, that is as a stage for other low temperature stages. But it should not be, the GM should not be dismissed out of hand, just because there is this belief that it's much noisier. It's not that much noisier. Here is an example of a pulse tube. This is the pulse tube cold head here. There's a motor assembly that it controls a valve that converts the unidirectional flow in these flex lines to pulsating flow. And those connect the cold head to the compressor. So this is the same, actually the same compressor that I showed you before that is installed on Sophia. Two of them are installed. Here's a performance map. This is kind of difficult to get used to, but I'm just showing it to get an idea of the cooling capacities. These roughly vertical lines are lines of constant cooling capacity on the first stage, the warmer stage. The roughly horizontal lines are lines of constant cooling capacity on the colder second stage. And then we have the temperatures on the first and second stages. So it's possible to read off based on how much heat you're putting on the two stages, what the temperatures should be, and vice versa. As long as that curve is, as long as that performance map is well calibrated, that is. Now the transmit pulse tube is very similar. It has basically the same specs as the Cryomac I just showed you. This was used, this is the only pulse tube actually that's been used so far, used in Great. It was going to be used in Hermes. And let's just give some specs. Now here we get into the tilt dependence of a pulse tube. And this was measured at Goddard using the pulse tubes that they bought for the Hermes, I believe. So the magenta line here is the temperature of the colder second stage. It's supposed to be colder anyway, as a function of tilt angle from the vertical. The blue line here is the temperature as a function of tilt angle of the first stage. And you can see there is some dependence. It's not terrible between minus 20 and 20, which is what it has to cover. You get out beyond 30 degrees, it kind of goes nuts. You don't want to go out there. In operation, the orientation will vary between minus 20 and 20 degrees, as indicated by these vertical lines here. During thermal testing, the pulse tubes are run at 20 degrees tilt. Sort of builds in some, automatically builds in some margin. Now the oscillation pot, this has never been used and probably never will be, so we won't talk about that one. And that does it for the pulse tubes and GMs. So if there are any questions regarding those, now would be the time. Before we get into the sorption refrigerators.
Just giving everybody a second since the stream is just slightly behind, but no questions at the moment.
Well, the pulse tubes were fairly straightforward. Sorption refrigerators. Now these are very useful little things. They're small, they're low mass, and they're highly reliable. There are no moving parts in them. And they can provide moderate cooling capacities up to 300 microwatts at 1 Kelvin using helium-4, and up to about 30 microwatts at 300 millikelvin. That would be using helium-3. They're typically single shot. They must be recycled periodically. but they have a high duty cycle of up to 95%. It is possible to configure them with multiple evaporators and absorption pumps to provide continuous cooling. But for Sophia, it's not necessary because single shot refrigerators are capable of providing cooling throughout the observation phase of a Sophia flight. So we're not considering continuous versions here. So they can be used for a lot of things. They can be used for intercepting heat leaks. They can be used as pre-cooling stages for a dilution refrigerator or a magnetic refrigerator, for that matter. They do have flight heritage on Sophia and in space as well, I should say. Helium-4 refrigerator was used to pre-cool the ADR on Hawk Plus. Hermes would have used both helium-3 and helium-4 absorption refrigerators. And it's a very good thing. So this is basically how they work. You start with just a helium pot here. Has some liquid in it. If you pump on it, it'll get colder. It's just evaporative cooling. And the temperature you get to is a function of the pressure you get to. So you just follow this saturated vapor pressure versus temperature curve down to give you the temperatures. So the red dots are for helium-4, the blue are for helium-3. So to get a absorption refrigerator, all you have to do is replace this vacuum pump with a absorption pump. And we'll show that on the next page. There's a very simple schematic of a absorption refrigerator, and it has just a few components. The most important component is the evaporator. This is where you condense liquid, either helium-3 or helium-4. In this case, it would be helium-4. And up here, one is the absorption pump. It's filled with charcoal, which is a very good cryogenic adsorbent for helium. There's a pumping line in between. This is staged off of some temperature, usually 4 Kelvin. And then there's a heat switch, which connects the cold plate with the absorption pump. And there's a heater also. So what you do to start this up is you heat it up with this heater. That forces all of the helium out of the adsorbent down into the evaporator. And there's a condenser here that causes the condensation so that you get liquid helium down in the evaporator. Once you do that, you turn off the heater and you turn on this heat switch here. And that provides a heat path from the absorption pump to the cold plate. So that cools down the adsorbent. When you do that, you start to adsorb helium. So that's the pumping action you get. And it'll continue to pump until you run out of liquid and everything is adsorbed. So like I said, there are no moving parts. Typically the cold sink, 5, would be in thermal contact with the helium bath or the second stage of a pulse tube or GM at 4K, slightly colder. For helium-3, there's a problem. The problem is that it won't condense at 4 Kelvin. You have to be slightly colder. So you might need a helium-4 refrigerator, absorption refrigerator, to just to condense the helium-3. Liquid in the evaporator is usually contained by some sort of porous medium, such as copper sinter. That would actually allow it to operate in microgravity, and would certainly help with operation under tilt in any SOFIA application. In fact, they haven't had any problems with tilting these things. So this is the absorption mechanism. At some high temperature, you'll get very little absorption. As you cool it down, you get more and more. And for very cold temperatures, you get almost total absorption. And rate of desorption, well, first of all, the adsorption is the adhesion of atoms or molecules to the surface by a van der Waals force. And there's a van der Waals binding energy, gamma. And the rate of desorption per time is proportional to this factor. It's analogous, really, to evaporation, where gamma then would be analogous to the latent heat. So it's like a latent heat. Pressure is proportional to the surface coverage and desorption rate. So why do we use charcoal? Well, it has a very high binding energy relative to other things like metals. As a vapor pressure above 1 or 2 monolayer films is extremely low at low temperatures. Charcoal has an extremely large specific area. So you take 1 gram of charcoal, there's 1,000 to 1,600 square meters of surface area, which seems pretty incredible. 1 helium monolayer is 13 micromoles per square meter. And 1 gram, so 1 gram of charcoal can absorb up to 0.02 moles of helium. Absorption refrigerator capacity. So the energy capacity per cubic centimeter of liquid is given by the latent heat times the density. So, and then you can turn that into a cooling power over the cooling time. Just by dividing the energy density by the hold time. So that's about all I have to say about that, I guess. We can talk about a neat example. This is the IRTS helium-3 sorption refrigerator. This was for the IRTS, the Infrared Telescope for Space. It was the first Japanese telescope dedicated to infrared astronomy. It has a cooling capacity of 15 microwatts at 0.3 Kelvin, and it can run for 8 days at that level. Recycle time is 15 hours. That's a 93% duty cycle. And total mass, 870 grams. And you can see the centimeter scale here as well. So I've already showed you in a previous slide the various components. So this was built for microgravity operation. There's some sort of porous material in here. I'm not sure exactly what it is. But it has to be very fine pores because helium-3 is a very low surface tension. Something you have to keep in mind. Here's the performance on orbit, period of 7 days. Worked very reliably, although this step at 4 days is unexplained. He also sent helium-4 sorption cooler and a helium-3 sorption cooler up in a sounding rocket. So for a period of 500 seconds, they both ran. And the arrows indicate various events in the flight from liftoff to reentry. Okay. Here's another example, and this is a commercial one built by Chase Research Cryogenics, helium-4 sorption refrigerator. This is shown upside down. The sorption pump is on the bottom in this drawing. And then you've got the helium-4 cold head. It's a very simple, compact unit and very reliable. These, by the way, are the sorption refrigerators that were used for Hawk Plus and Hermes, or Chase Research sorption refrigerators. And there's a nice cooling curve for cold head. Now, going to helium-3, I mentioned this before, helium-3 does not condense at 4 Kelvin. So you can't quite do the same thing unless you've got a 3 Kelvin heat sink, which you usually don't. So in this case, it makes sense to package a helium-3 sorption refrigerator with a helium-4 sorption refrigerator. And the main purpose of the helium-4 sorption refrigerator is to provide cooling at this condensation flange, about 1 Kelvin. So as you're recycling this cryopump here, this sorption pump, the helium-3 will come down this tube and get to this point and condense. So you get liquid helium-3 in the evaporator. And you can run it down to 0.3 Kelvin or below. And here is one of these tandem helium-4, helium-3 sorption refrigerators. Again, it's a Chase Research unit. And on the right is the load curve for the helium-3 head. Quite a bit, 100 microwatts at 0.34 Kelvin. That's quite a bit of heat, cooling capacity. So that's it for the sorption refrigerators. Any questions on that section? If not, we
still no questions.
Okay.
So
we can move on to finally. I've been talking about ADRs all this time, and haven't explained yet what they are. An ADR is very efficient and reliable in the sense that it's all solid state, no moving parts. Again, like the sorption refrigerators. Operate above a very wide temperature range from above 6 Kelvin to below 50 millikelvin. Depends on the salt pill material, heat sink temperature, and the size of the magnet. But it's quite simple in principle. It's only a few components. There's the salt pill here, or it's sometimes called the refrigerant. That's the thing that gets cold and is directly thermally attached to the thermal load, thing you want to cool. It's surrounded by, well, it's sitting in the bore of a superconducting magnet that allows it to be magnetized and demagnetized. And then there's a heat switch to connecting it and disconnecting it from a heat sink. It's usually, typical cooling capacities are 1 to 10 milliwatts in the 1 to 4 Kelvin operating range. That drops dramatically, drops down to a few microwatts, as I've said a few times so far. A few microwatts below 100 millikelvin. There's usually there's single stage, single cycle. But multi-stage ADRs can be configured to provide continuous cooling. Now, for SOFIA applications, the operating temperature would be less than 200 millikelvin, hopefully. It should be, usually they're designed to go below 100 millikelvin. With a capacity of around 2 microwatts and a hold time of 10 to 16 hours. This is with, as was seen with the Hawk Plus and the Hermes ADRs. Because of the relatively short observation time, it doesn't really make sense to look at anything but single shot ADRs in this report. Another advantage of the ADR is that it's gravity independent. It's insensitive to cryostat tilt. One drawback, which I didn't mention here, is the magnetic field. Sometimes you need a lot of magnetic shielding. So the refrigerant, the salt pill, is basically a three-dimensional array of magnetic spins. And this is used to, it's sort of like a thermal sponge. And the way you'd absorb heat is you'd have to magnetize it, as here on the right. And you do that by wrapping up the magnet. And then you'd demagnetize it adiabatically. This then would be in contact with the load, the thing you want to cool. And so heat will go from the load into the salt pill, and that thermal energy will tend to randomize. Well, won't tend to, it will randomize these individual spins. So as it warms up, it becomes more and more random. The entropy increases towards a maximum, which is what you get here. These spins are completely randomized at this point. And at that point, you won't get any more cooling out of it. You have to recycle. So the pill material, refrigerant, should have a high magnetic moment and high density. Ideally, it should be composed of a system of non-interacting spins. In reality, there will be some interaction, and there will be a transition temperature where the system will spontaneously order. And that's shown down here as Tn. These are various salt pill materials. Now, so ideally, in normal operation, the ADR of the ADR, the ordering is field induced. So it's the magnet that's ordering it, and what's deordering it is the thermal energy collected from the load. Here are, well, this is kind of a confusing chart, but it's just lines of constant magnetic field. So it's so confusing, we'll go to the next one. So again, these are lines of constant magnetic field. This is B equals 0. As you increase the field, these lines move up to higher temperatures. So this one, for example, is 1 Tesla. So the refrigerator goes through this cycle, A, B, C, D, E, back to A. Now A, you're starting here at the temperature of the of your heat sink, and you'd want to turn on the thermal switch between the heat sink and the salt pill here. And what you do is you then magnetize the salt pill by ramping up the magnet. This is all done isothermally at the sink temperature. So this is where you wring out the heat that you've absorbed at lower temperatures. When you get to this point, you turn off the switch, the thermal switch. So you decouple the salt pill from the heat sink, and then you, at constant entropy or adiabatically, you demagnetize. So this is the adiabatic demagnetization, the AD and the ADR. When you get to B equals 0, you'll start to absorb heat from your load, and this will just warm up and become more and more disordered. The entropy will approach a maximum, and will reach that maximum when it gets back to A. So it's in this point, this region here, where you're actually absorbing heat. And here is where you're wringing it out. So, and this can be recycled indefinitely. Like I said, for an adiabatic ADR on Hermes, you're not going to be recycling it during an observation period. It'll be just a single cycle. The other thing that should be noted here is that once you get to C and it starts to warm up, it does not maintain a constant temperature. Temperature is increasing as it's absorbing heat. Now, the other thing you could do, and in fact, this is what they do, is instead of demagnetizing all the way to B equals 0, you could demagnetize to some intermediate field, see here, and then it'll start to warm up, and you can use that reserve field, the remaining field, to control the temperature. So you end up with something that looks very much like a rectangle, and actually very much like a Carnot refrigerator, which would trace out a rectangle on an entropy versus time plane. So that's the basic idea of how it works. Now, the paramagnetic salt pill is not just the salt itself. What makes it so complicated is that you have to get the heat in and out of it, and it's not a very good thermal conductor, so you have to have a thermal bus that looks something like this. And this is composed of very fine wires or ribbons of copper, and the salt, the refrigerant, is grown on this bus, and that can take days to weeks to do properly. XRS, this is something we'll be talking about in a couple of slides, uses 930 grams of FAA. It's the same materials used in the Hawk ADR as well as the Hermes ADR, about the same amount of refrigerant as well, around 900 grams. Here's some practical limits for ADRs based on designs for Sophia. Net cooling power, about a microwatt. So this is after you've subtracted off the parasitics from the gross cooling power. Operating temperature, 80 to 100 millikelvin by design. Hawk operated quite a bit warmer than that, up around 180. Heat sink temperature, around 1 Kelvin, which can be provided by a helium-4 absorption refrigerator. Magnetic field, 2 Tesla at a current of 2 amps. Refrigerant mass, about 900 grams of FAA. and a hold time of 16 hours, a recycle time of 5 hours. Some important trends. A higher heat sink temperature requires a higher magnetic field, and a lower operating temperature requires a higher magnetic field. But it's kind of hard to get to these high magnetic fields because you have to, well, you want to increase the mass of the refrigerant. That means you need a larger magnet, larger bore, and you need a larger magnet just to ramp up to a higher fields. So as you increase the field, the mass and size of the magnet starts to grow pretty rapidly. So these are really pretty practical limits for SOFIA ADR systems. This is XRS, the Astro E X-ray spectrometer, ADR. This is the salt pill with plumbing and stuff here. Not plumbing, but wiring. And a thermal bus. And this fits inside the bore of a superconducting magnet. The salt pill heat switch and suspension was built by Goddard. The superconducting magnet is a niobium titanium magnet built by Cryomagnetics. It has a 2 Tesla central field at 2 amps, 3-inch bore, 6 inches in length. And this was designed to operate in a helium bath at 1.5 K, so a pumped helium bath. Operating temperature was 60 millikelvin. Hold time 30 hours. And total mass was 15 kilograms. So a very good example of the sort of size of an ADR that you might put in a SOFIA SI. And we won't discuss this. Plus ADR. We pretty much said this already. Same with the Hermes ADR. Very similar. So that covers ADRs. Next, we'll go on to dilution refrigerators. And we might just have enough time to get through this. Are there any questions first before I move on?
Giving the chat 1 second to catch up to the stream, but I don't think we have any questions on ADRs. I'm glad you got to that because it was something I was curious about earlier when you described the salt pills and terminology for me.
Okay. So now we move on to dilution refrigerators. And of all the technologies we've discussed so far, this is one technology that has not flown on SOFIA. It could be a contender. Can take a lot of work though to develop something like this, but it could compete with an ADR. And I'm not going to go through all of this, but there are various types of what I call variants of dilution refrigerators. There's the helium-3 circulating warm cycle DR. There's a helium-3 single shot DR. There's a helium-3 cold cycle DR and a helium-4 cold cycle DR. And there are various different types of these variants as well. There's quite a large parameter space to consider if anyone was ever interested in trying to build a dilution refrigerator into a science instrument. So what happens in a dilution refrigerator is you've got a mixture of helium-3 and helium-4. And at high temperatures, these are miscible. So they're all mixed up. As you cool, though, you'll get to a point where this mixture spontaneously separates into two distinct phases. There's a concentrated helium-3 phase and a dilute mixture. And because the helium-3 is less dense than the helium-4, it floats on top of the helium-4. So this is the what's called the mixing chamber. And floating on top of this dilute solution here is the almost pure helium-3. And it works in a very similar way to a helium-3 pot. On a helium-3 pot, you just pump on the liquid and you reduce the vapor pressure above the liquid. And that lowers the temperature of the pot. In a mixing chamber of a dilution refrigerator, you're also pumping on helium-3, but you're pumping from the bottom. You're pumping helium-3 from this rich phase, helium-3 rich phase, to the dilute, through the dilute phase, and then out. So it's very similar, but they're very different temperature profiles. And the reason for that is that as you pump on a helium-3 pot, you're decreasing dramatically the pressure. Cooling power is proportional to the pressure, which is proportional to this exponential. So you get this exponential decrease of the cooling power of a helium-3 pot or a helium-4 pot, any liquid pot for that. But the nice thing about a dilution refrigerator is that the concentration of helium-3 in this dilute phase never goes to zero. And that gives a very different temperature profile. It gives a profile that's proportional to the square of the temperature, not through this whole range, but down, starting around 100 millikelvins. It's proportional to T squared, and it's proportional to the flow rate. So mixing chamber, like I said, is where the cooling takes place. It's just one component of the dilution refrigerator. This is a picture of a traditional wet refrigerator. The mixing chamber is down here. There's a series of heat exchangers. There's a helium-4 pot up here, which is used to condense the returning helium-3 stream. Thermal load is attached to the mixing chamber at the bottom, down here. The pump mixture moves upward through what's called the still. Right here, this is the condenser right here. This is the still. And it's pumped on by a helium-3 pump at room temperature. And then is returned back by this stream, which is why you need all these heat exchangers. That's the one of the drawbacks of a warm circulation system. You have to have all very good heat exchangers. So the returned helium-3 is condensed at the pumped helium-4 pot, which is maintained at around 1 Kelvin. The helium-4 pot is serviced by its own mechanical pump. The return stream is pre-cooled by exchanging heat with the outgoing stream at the still and the heat exchangers. And it reaches a temperature Ti. I stands for in, I guess. That's the temperature at which it goes back into the mixing chamber. And that lowers the overall cooling power. So that temperature depends completely on how good these heat exchangers are. This is similar, except it's a dry DI. So instead of a liquid nitrogen jacket with a liquid helium bath, we replace both of those with a two-stage pulse tube. So the first stage, which is here, cools this plate, which cools a large thermal radiation shield down around everything else. The second stage also cools a plate and full plate and another shield. And then down here, you've got the mixing chamber. This is the pumping line, which you can see is quite large. But this is for a very high capacity system. So it's hundreds of microwatts of cooling as opposed to a few microwatts of cooling that you need in a Soviet SI. Now, it's not inconceivable that a scaled down version of a dilution refrigerator like this could be done. But you'd need an external pump, a sealed helium-3 pump, as well as a return line. And it's, I know that the Sophia project would not be too happy to consider that idea. But this is a very good potential solution. This is a very simple and elegant single cycle DR that was developed by a former colleague of me and Ali Kashani at Roche, who was in our group, hired, I don't know, 10 years ago or something. But he developed this. This is a very compact unit. It just consists of 4 chambers and 3 charcoal pumps. And it's designed to fit inside the 6-inch bore of a helium duo. Obviously, you could use a 2-stage pulse tube to pre-cool it as well. You just connect this plate here with the second stage of the pulse tube. So, yeah, how this operates roughly is the helium-4 is condensed into the helium-4 pot. This is the helium-4 pot. And then it's pumped on by a sorption pump right here. I'm not sure which one it is, but one of these is the sorption pump that goes with the helium-4 pot. And as that pumps it, gets it down to about 1 Kelvin. That's cold enough to allow for a condensation of helium-3 in the helium-3 pot, which is here. Condenser, which is in very close thermal contact with the mixing chamber. So the mixing chamber, along with the still, has its own charcoal pump. The charcoal pump for the condenser, one for the helium-4 pot, and one for the, it's called the still here, which is where you pump out the helium-3 from the mixing chamber. So that's how, so once you get everything condensed, you start pumping on the mixing chamber, rather on the still, and that will cool. This particular model ran for 10 hours at 20 millikelvin with a heat load of 1 microwatt, which is really good. You see also on this plot that the correspondence to the theoretical T-squared temperature dependence. Requires about, so this is a very simple system, and I would say it would be the front runner, except maybe for one problem. That is that it requires a lot of helium-3. So you need about 1 cubic centimeter of liquid helium-3 for 1 hour of runtime. So if you need 15 hours of runtime, that inventory of helium-3 really mounts. And in addition, the size of these chambers increases as well and become heavier. And that makes it more difficult to control vibrational heating. So that's the only real drawback to this. This is another very similar single cycle ER, but this one was designed to tilt. It was designed for balloon-borne astrophysical applications. I don't believe it was ever used. But it is a tiltable dilution refrigerator, and it operates in basically the same way as the one I just showed you. It's a single shot, single cycle. The cooling power of 1 microwatt was measured at tilts of both 0 degrees and 30 degrees. If you look here, 2 microwatts at about, 90 millikelvin. 1 microwatt at about 80 millikelvin, which is pretty good too. So that rivals the ADRs that have been used on Sophia. The ADR that was used, only one. Another thing you can do is have a cold cycle DI. Now these are continuously running. They provide continuous cooling. Now the continuous cooling is not really necessary because of the limited observation time. The advantage of it is that it greatly reduces the inventory of helium-3 that you need. This particular one uses 2 charcoal pumps, which are reciprocating. One is pumping on the still in the mixing chamber, while the other is recycling via a condenser. And when that's done recycling, it starts pumping, and the other one starts recycling. So back and forth for as long as you want. This on the right, this dilution refrigerator was also developed by Pat Roach. He developed the RMC refrigerator here. This was designed for microgravity operation. That's why I have all this porous media in here, the mixing chamber, condenser, still. And this is driven, in a sense, passively. There's no pump here, like there is here. There is a pumping, and that's because there's an osmotic pressure that develops between the mixing chamber and the still. So that's enough to move helium-3 out of the mixing chamber into the still. And then you have cryo pumping at the condenser. So you've got helium gas then evaporating off the still, going back into the condenser, back into the mixing chamber. So, and that goes on forever. So this could also be a very attractive option for Sophia. Probably would be the smallest of the options that we've looked at. And there actually is a commercial model. Well, I don't think this is an off-the-shelf model, but it's from, it was built by Chase Research Cryogenics, the same company that built the absorption refrigerator, as I showed you before. This is capable of cooling below 100 millikelvin with a load of 3 microwatts. And it only uses 3 liters STP of helium-3. So this was used for a large millimeter telescope. And this refrigerator was built, I believe, specifically for that application. Well, this would be a very promising thing to look at if an instrument designer were to be interested in trying out a dilution refrigerator instead of an ADR. And then finally, this is the Planck dilution refrigerator. This flew in space. I'm just putting it here for it's the only because it's the only dilution refrigerator to have flown, whether in space around Sophia. It has a very low cooling power, 0.2 microwatts, 100 millikelvin. But the real problem with this is that it's an open cycle system, meaning that the helium mixture, including the helium-3, which is a very precious commodity, is vented to space. And once it's all vented, it stops running. It ran successfully for 2.6 years. And now it is dead. Okay. So I think that's all for, all for the dilution refrigerators. And we're right on time.
We do have a question on this one. Monica asked about slide 85, if you could use an SI. Could an SI use a dry DR and then use the Sophia cryocooler system to do the first 2 PT stages?
Well, you would use, yes, exactly. You would use the Sophia cryocooler system to drive the pulse tube or pulse tubes if more than one is required. So yes, the answer to that is yes. And like I said, it's possible that you could build a scaled down version of this. This thing is really enormous. You never fit it inside of an SI. But if you scale it down, it could work. The only problem is this is a warm circulating dilution refrigerator. You need an external pump, a sealed helium-3 pump. So a pumping line and then a return line coming back. So it's conceivable that something like this could work and might even be able to provide a lot of cooling power. But it's unlikely that the Sophia project would okay something like this because of the modifications that would have to be done.
Thank you. That was a great answer, and I think that's the only question for this section.
Okay, great. Great. Now we are almost done. We'll just say a little bit about thermal switches. And we've run into thermal switches before in the context of ADRs and absorption refrigerators. For the developer, there's some important factors to consider in the selection of the switch. And there are many different varieties. We'll only look at a couple different types here. But so the developer should look at its operating range, of course, temperature range, on-off switching ratio, that is on conductance versus the off conductance, how quickly it can switch as well. The actuation method, reliability and thermal dissipation there. Excuse me. Mass and size, of course. Sensitivity to vibrational loads, pretty low. Its sensitivity to tilt, that's pretty good. And availability, most of the variants discussed are commercially available. And here's just a list. We won't talk about these except for a couple. But it gives a list of different types of thermal switches and their range of applicability. The most common, I think probably by far, is the active helium-3 gas gap switch. Although mechanical switches are used a lot too, I guess. Here's a mechanical switch, and it's actually the type of switch that Hermes would have used. Hawk Plus used a gas gap heat switch. I'm not sure what determined the selection of a mechanical switch in this case, but it works very well. It's got a very high on-off conductance ratio. Well, it's actuated by, can be actuated, in Hermes, I think it was actuated by a stepper motor. But you can also use piezoelectric or magnetostrictive actuators, shape memory alloys, whatever those are. Now, the main type of heat switch is a gas gap heat switch. And rather than reading through this, we'll just go to a simple picture since we're running out of time. This is two halves to it. So if you look at this section here, which extends down the length of the tube on both sides, and this section here, which also extends on the length of the tube, they don't actually touch. There's a very narrow gap, about 100 microns in between those two. So if there's no gas in that gap, then it won't conduct. There will be some conduction along this thin stainless steel tube or titanium alloy. But that's very small. That's quite small compared with the on conduction. Now you turn it on by heating up this little getter, and this is a miniature absorption pump here. This is, so we've got helium absorbed here. And you heat it up, that forces the helium out into the gap. That provides then a thermal path between this end of the heat switch to this end. Turn it off, you just turn off the heater again, that cools down, and the helium is absorbed. Heat capacity of the getter and thermal conductance of the capillary tube determine the turnoff time. It's usually only about a minute, which usually does not present a problem. Here's a nice example of a gas gap heat switch. Here, it's kind of hard to see, but this is a sort of interleaving gap right here between the two halves, between the two ends of the heat switch. And the other interesting thing about this is that the shell, instead of thin wall stainless or something else, is a titanium alloy that I believe goes superconducting. Yeah, it does. It becomes superconducting. And the thing about a superconductor is it's a very poor thermal conductor. So that's a way of ensuring a very good off thermal resistance, off-state thermal resistance. this was designed and built at Goddard. Now, this, I think, is the last slide. I don't really want to talk about passive gas gap heat switches. I just wanted to show this interleaving, which is more common than, which is sort of a common geometry. Here you see an example, the two halves of the heat switch. Here completely disassembled. Here the two halves are interleaved, and here the whole thing is assembled. Well, that's about all I want to say about heat switches. I'll talk about thermal straps, but I think we're about out of time. Not much to say about this, but I wanted to get to the last slide, which is sort of a recapitulation, but it's more general guidance concerning SI cryostat designs. So number one, the SI developer should adhere to established best practices in cryostat design and fabrication. Yeah, it's sort of a given. Two, the design process should begin with a clear understanding of the instrument's thermal requirements, including desired goals and acceptable limits. And all of SOFIA specific constraints, including size, mass, center of gravity, safety, etc. For sub 1K cryostat, special attention must be devoted to the vibrational environment. Number three, thorough trade studies should be conducted, including a wide range of available technologies, at least those technologies it's discussed in this document. Four, perform quantitative mechanical analyses. It's normal mode analyses, forced vibration analyses as design and build proceeds. And an engineer with experience in this field should be brought on as soon as possible. Number five, no amount of analysis or modeling can substitute for testing in a relevant environment. So you should start a rigorous test campaign as soon as it's practicable. Components and assemblies should be tested in a simulated SOFIA vibrational environment as soon as feasible. Six, conservative thermal margins should be established. Now, the thing about thermal margins at these temperatures, it's kind of hard to deal with. At higher temperatures, you have standard margin schemes. Goddard, JPL, military has them. But when you get to very low temperatures, it's kind of difficult to systematize thermal margins. It's because of heavily design-dependent factors like parasitics, which can be comparable to the gross refrigeration capacity. And there are also large variations in materials properties. The thermal conductivity of copper, for example, or aluminum. So that's about all I wanted to say. Well, I wanted to say more, but that's all the time I had.
It's hard when there's so much information to provide with all your experience.
Well, I'm surprised I came in right on time, right?
It was perfect.
I don't know how that happened.
Well, I don't think we have any final questions, and we are right at the end of time, but really thank you so much for this presentation. I have a lot of notes to myself. I'm like trying to watch the questions, but also take notes, but really appreciate you taking your time and providing all of this information to us. Thank you for being here.
Oh, okay. Thank you. It's been fun.